pointer. So today we're going to talk about evaluation of analytical data. So for some of you this is a very easy topic. For some of you you need a refresher. For some of you it might be altogether new. We'll see. Okay. So knowledge check. So if a method is more precise in measuring, let's say, glucose content than method B, which one of these answers are correct, Josie?
I'd say just A.
A. Any different answer than A?
B.
Wait. A and C. Any other answers? Sven? E. So you like the C, it seems like. No. It's just A. Okay, so when we talk about precision, we're going to learn two terms today, standard deviation and coefficient of variation. This is how these two measures allow us to determine how close our replications are. What's the level of variation we have between the replication of the same sample we are analyzing. However, C has to do with, not precision, what's the other term that C? Nicole?
Accuracy.
Accuracy. Okay. So if you want to answer, raise your hand so that you can get the +2. Okay.
It's somewhere in the back, too.
What's that?
There's some hands in the back.
I'll get the back next time. Okay. All right, so let's go over how do we evaluate our data. The first thing we do usually is we have our replication and we look at two measures. We call them central tendency. And this is probably, I'm taking you back to probably 8th grade now or 7th grade. But you have the mean and the median. So the mean is your average and the median is, yeah, Jim?
The middle number of your set of data.
Yeah, so the middle number of the set of data. So these are the most common measures. In this class, we're going to deal mostly, if not totally, with the mean. We're not going to worry about the median. And then we're going to look at reliability of our analysis. How precise is our analysis? How accurate is our analysis? We're going to look at errors too. Sources of errors and how these errors contribute to our results, so that errors can both affect precision and accuracy, right? Specificity. How specific is your method, right? We said that last time. So are we measuring total carbohydrate or measuring glucose, for example? And then sensitivity and detection limit. Do you know the difference? Okay, Aaron.
The sensitivity has to do with like the minimum amount that has to be present for it to be detected. And detection limit is like the maximum amount.
Sarah?
Is sensitivity like the magnitude of change that instrument can detect?
Yes. Sensitivity is the magnitude of change. How sensitive is, what's the smallest change that can be detected by a certain method? So it is 1.2 parts per million, so, and then it can detect 0.2 parts per million difference. So if you have 1.2, it can be significantly different than 1.4. The instrument can tell you that 1.2 is different than 1.4. So that's sensitivity. Detection limit is, Aaron, what you said earlier, it's how the threshold, how low can you go to detect a signal that is not noise. Most often during our labs and the calculation of data, you'll be generating something we call standard curve. So we fit the data to a linear regression. Most, if not all of our analyses are going to be linear regression analysis. So how well the data correlate with each other to unfit a straight line, basically. So we do linear regression and we look at coefficient or R squared, and this correlation coefficient is R, but there is regression coefficient, which is the R squared, which tells you how well you can do prediction, okay, using the standard curve. And of course, there are errors associated with it. We're going to spend some time also reporting results. Significant figure is a big thing, and students oftentimes have a lot of mistakes reporting significant figures. So when you calculate a number and you have 10 digits after the decimal, you don't want to see this in your table of results. You have to report what is supposed to be your significant number of figures based on the analysis that you run. And we'll spend some time today on this for a little bit, and also in the lab a lot next week, talking about significant figure and how you report them. And also sometimes you have to reject the data, otherwise it's going to skew your results. So sometimes you have, let's say, 6 replication, one of these reps are really off, either really very low or really very high compared to the other set. So there is a measure, we call it the Q test, that you would do to reject the data, remove it so that it doesn't skew your mean. Because if your mean is skewed, then your accuracy would be wrong. So you would determine an average that is far from the accurate number or the true value of your analysis. Okay, so pull out a piece of paper. I want you to start, write your name on the top, and then we'll do a series of calculations, and then you hand that paper in for a +2 at the end. That's one of your extra credits. Okay, so here you have, you've determined moisture content of a sample, and you measured the moisture content 5 times. You had 5 replications. So determine the mean and the median. Can use obviously calculators. Okay, when you have a value, let me know. Yes, Michelle?
For the mean, it's 82.56.
Yeah, and the median, you had that next time. Okay, so that's easy. You all know obviously how to determine the mean, and the median is the midpoint. All right. Look at all these 4 different options and tell me A is which one of these? Okay, I see anybody from the back row? Amanda?
Good precision, bad accuracy.
The first one is good precision, bad accuracy. Somebody else? Ben, you had another? Okay, so I saw hands up here for the second one. Erica?
Good precision and good accuracy.
Perfect. C? Agnes?
Bad precision and bad accuracy.
That is terrible. Whoever did that is horrible. Okay, what about D? Claire?
Good accuracy, bad precision.
Yes, good accuracy, bad precision. Obviously, when you're right here in the bullseye here, with all of the values close to each other, that's where you want to be. That's your best bet. Here, you're having a bad day. It could be, we call it sometimes Monday morning syndrome. Those of you that are in Monday lab, you might witness this at some point. So, yeah, here in this case, your precision, something is off with your experimental error. However, somehow they're evening out and you're getting close to the true value. Here, there could be a systematic error. We're going to talk about the different errors. Systematic error could be your pipette is not calibrated. So you're always pipetting 0.8 milliliter, for example, instead of 1 ml. So you're always getting, you're off, you're not accurate, but you're always getting good precision. So things like that you have to kind of troubleshoot to see how you can get to the B option. All right, so accuracy, how do we determine accuracy? So there is something called determining absolute error, which is the difference of your average. So you have 4 replication, 5 replication, what have you, and you determine the average. And this would be your true value. It could be a reference value. It could be somebody did a service for you and followed an official method of analysis and gave you the true value. It could be a published value. So that would be your true value. You would use it as a resource, and then you look at your average that you've generated in the lab, and then you determine absolute error. But oftentimes we don't just determine absolute error. We determine a percent relative error. That means relative to the true value. So the difference relative to the true value. How far off are you in percentage-wise from the true value? Are you 20% off? Are you 5% off? That would be great if you're just 5% off. 5% and less is kind of rule of thumb. You're good. 10% or less sometimes is also acceptable. But if you're 50% off, that's really bad. All right, let's do some calculations. So in this case, you're using a mechanical pipette, which you will be using in the lab next week, to measure 1 milliliter. And then you've taken these different readings, and this should be, sorry, I'm missing, 3 readings in milliliters. So there's your unit. Yeah.
Do you report the error in like negative values?
No, it's always in absolute. So always you have absolute value, the difference in absolute. And Jesse, right? So you got it in? Oh, okay. All right, so whenever you have values, let me know. All right, Ben, you're done with all of them?
No.
What do you have? Average?
Yeah, it's 0.9 is 1.
Okay, what's your true value in this case?
We don't know, right?
We know. Bailey,
1.
1 is your true value because the pipette is telling you you're pipetting 1 ml. Okay? So that's your true value. All right, so basically you get the average, you get the difference, that would be your absolute error. Then your relative error would be the difference over the true value, that would be 1 in this case, and then you multiply by 100. Okay? Make sure you complete that so that you get your extra credit, and I'll move on, I'll give you a minute. I'll continue when I see heads up. Okay, are we guys ready? Moving on. So, did you all get these values? Well, okay, forget. Who asked this question? It should be an absolute, not negative. Negative tells you which direction really, it's lower or higher. But usually you don't report the negative here. Okay? So are we all good? Yeah?
I'm sorry, did you say the absolute should be positive?
Yeah, so forget about the negative here, it's just the difference. Usually, it's
For
just
both?
the negative is just telling you which direction. It's slower than the true
For all
value.
of them or just the absolute?
Not for all, for all of them. But the negative here is again just telling you which direction it's different. All right, so let's talk about precision. So you need to know this equation. Okay, this is a simple equation to remember, and you will be asked to calculate standard deviation and coefficient of variation in a quiz or exam. So you need to know this. I know Excel nowadays produces it, but it's always good to know how these values are popping up for you. Okay? So standard deviation is the square root of the sum of the difference between each value and the mean. So this would be your mean. It has a bar here, it should be a little bit lower, but that's your average, and that's any point, any one of your replication. And n is your number of replications. So if you have a 4, then n minus 1 is a 3, and so on. Okay? So it's a really simple equation to remember, not that hard. Now, coefficient of variation sometimes is more meaningful than a standard of deviation. And then I'll give you an example why is that. But for now, coefficient of variation, it takes into account your average. So you have your standard deviation and you divide it by the average and you multiply by 100. Here you are standardizing your variation based on the size of your mean. So if your size of the mean is 100 versus 100 grams versus 1 gram, now you are standardizing this difference by taking into account the mean. And then you multiply by 100. And again, the rule of thumb is anything less than 5% coefficient of variation is really good. But sometimes your experiments have multiple steps, like 15, 20 different steps. Very tedious. We'll go, if you get less than 10% coefficient of variation is still good, depending on the method that you are following. Okay? So what I want to do now is give you an example. I have a few numbers here to show you. Let's say, do we have any markers? Okay, let's say we have wheat flour. And you used IR, near IR, let's say, instrument to determine protein content. Percent. And you got a value of 12%, and your standard deviation is plus minus 1.2. Okay? And then you got another sample. Let's say you have soy protein isolate product, and you determine protein content using a Dumas method, which you will learn in the lab. So you got 92%, and you got a standard deviation of 2.76. All right, if you look, compare here and here, which method is more precise? And
The NIR method.
Andy says this is more precise. Is this correct? Do you agree with Andy? John is agreeing with Andy. Aaron is agreeing with Andy. It seems all the guys in the room are agreeing with Andy. And all the guys in the room is wrong. Don't you like this, ladies? Yes, you guys are wrong. Okay, let's convert standard deviation to coefficient of variation. Can you do the math really quick? What would be the CV on this one? 10%. Okay, what would be the CV on this one? Yes, sir. 3%. Now, which is more precise? Yes, Agnes? What's that? Yes, because now your coefficient of variation is less than 5%. What happened? Look, this is a mean that is small, smaller than this mean. So when you correct for the size of the mean, you get the correct precision conclusion. So 1.2 seems smaller than this, but once you divide it by 12, you get a 10% coefficient variation. But this seems larger, but you are dividing it by a larger mean, therefore you end up with a smaller CV. So when you're comparing precision across something that is really different, you have to account for the size of the mean. But if you're comparing precision within methods on the same sample, so let me convert this. I'm going to say I'm using Dumas for wheat. Okay, so the sample is wheat, and I've got here, let's say 12 plus or minus 1.5, which is not true. In real life, Dumas is very precise. But in this case, you don't need to calculate coefficient of variation. Okay, you have similar means. The standard deviation is enough. You can say, okay, this method is more precise than this method, which is not necessarily true in real life, but just for the sake of example. Okay? Good. Leave it. All right. Another statistics number that you would calculate is something called confidence limit. So what's the confidence? Where does your value lie within a certain confidence interval? So usually you calculate that by this equation. So this is the range of your data, basically. Where is the range of the data falling? And usually you determine that with a 90% confidence or a 95% confidence. Often it's a 95% confidence that you look for. Okay? So it's basically your mean plus or minus t-value. You use a t-value when you have replication less than 25. If you have replications greater than 25, you use z-value. And then you multiply standard deviation over the square root of the replication. In other words, is called what? Does any of you remember what that? If you look at this only. Standard deviation divided by the root of number of replication. Other than standard deviation, if any of you have ever prepared a bar chart, a chart with bars, and then you have...
Is it percent relative error?
Yes. It's a relative error. In this case, it's not a percentage, but it's your standard relative error. So that would be standard deviation over root of number of replication. But anyway, how do we get the t? So if you go to page 58 in your textbook, 58 in the textbook. I'll get you that in a minute because you need it for a calculation. Okay, so you have a table on page 58 for t-values. So usually you look for the degree of freedom, which is the number of replication minus 1 is your degree of freedom. So you search for your degree of freedom and you go for 95% confidence interval, confidence that is, and then you get the t-value for a specific equation that you have to fill. Okay, so let's give an example and I'll give you the t-value from that table. Okay, so here in this case you have 3 replications. So your degrees of freedom is 2. So you have 2, and let's say you want 95% confidence. So your t-value, and you want to use t because your application is less than 25. So your t-value in this case is 4.3. So write that down because you need it for the calculation. 4.3 is your t-value. Ready with an answer? Yes, Vadi.
0.99
Okay, that's your mean standard deviation.
standard deviation.
You haven't gotten that yet? Yeah, mean we all know now that you guys know how to calculate the mean. Let's get these values in. You got, what do you have? Do you have them all?
0.0019.
Okay, that's 0.003.
0.0019.
Okay, that's which one is that?
Standard
And coefficient variation? Still working on it?
coefficient variation is just
What do you have?
Coefficient is 0.19%.
Okay. And then confidence interval, anybody? You have it too?
Yeah, 0.9961 plus or minus 0.0047.
Yes. And then you must have some bigger number here to round. So yeah, so these are your values. Make sure you have them correct. You'll be measuring all of this in the lab next week, and this is how you want to report your confidence interval, plus or minus. So if you go back here, so you calculate this value, t times your standard error, and then plus or minus this value is your confidence interval. So your true mean, in this case, you're 95% confident that your true mean lies within this range. Okay? That's what's confidence interval mean. Okay? All right. Questions? Would you like me to repeat anything? Okay. Sources of errors. So there are quite a bit of creative way to get to make mistakes. It's infinite, actually, the things that things can go wrong. But there are three major categories for errors. There is also a list of sources of error in your laboratory manual packet that it would be helpful to look at because it will help during the lab next week. Anyway, so you have something called systematic error. That means I just told you earlier that you're always getting something consistently wrong. Like a balance is off, or a pipette is off, or your method of pipetting is off. So when you use a mechanical pipette, there's a certain technique. If you don't do it and you always do it in a certain wrong way, then you're always going to get that same systematic error. So your results are consistently deviating from your true, however, they might be very, very precise. So you would go, oh, I'm not doing anything wrong. Look at my data, it's very precise, but it doesn't make sense. Then you go back and search for the error that caused this hidden mistake. Another major category, and this is more significant than, not necessarily more significant, more common than the systematic error, is called the random error. And usually if you do statistics and you analyze, you have a table of ANOVA, there's always an entry for error, experimental error. So this lies mostly here. Because this can, like if Amy is running the experiment versus Chelsea, there might be a different set of errors. I'm not going to say which direction it's going to be. I'm not saying it. Okay, so it depends on the person that is running the method. Their specific technique is causing a certain error. Okay, and it could be due to using different balances for the same experiment. So you will see that when you go in to do the ash or fat lab, we specifically label the balance that you used for a certain analysis so that you come the next morning after drying your sample to weigh using the same balance. Because if you use different balance, each balance is basically different, have different sensitivity, are calibrated a little bit differently. So you want to avoid such kind of errors. So they're random. They can be any number of different types of error. There's a list, and we'll go over some of them next week as well in the lab. Blunders. Big screw up. Like I mentioned earlier this morning in the lab, some of the blunders could be titrating with acid instead of titrating with base. Or instead of preparing 1 molar NOA or 0.1 molar NOH to titrate, you prepared 1 molar NOH to titrate, and then you just put 1 drop and the color changes quickly to pink. Or you prepare 0.01 molar and then you pipette and titrate and nothing happens. So that's called Monday morning syndrome, we call it, or blunders. That doesn't mean that the Wednesday group is not going to have blunders. I'm sure there are going to be a lot of those. Amy, you wanted to say anything?
Oh, I was thinking about my blunder on Friday.
What was it? Share it with them. It's funny. You had another blunder that you had where you didn't have the gas cylinder.
Yeah, that was the blunder.
I wasn't there. Okay, go ahead. Share it.
Well, when you run GC, you have to have gases hooked up because that's what it's based on, essentially.
Gas chromatography,
Yeah.
so you need gas.
Yeah, and I was wondering why the flame wasn't lighting for the flame ionization detector. Well, Gary came in and he just goes, your gases aren't connected, Amy. So that was my blunder.
Okay. All right. It's kind of like a check. So we've talked about this before. Let's see if you remember. Which of the following implies sensitivity? Yes, Ray? C. I'm going to say yes and not bother anybody else. So detection of minor change in constituent. So what's the minimum difference that the machine can detect between the 2 different samples or more? Okay? Standard curves. Like I said, a lot of the calculations in the lab is going to involve creating standard curves and using the equation of the line to predict unknown concentrations. So you will be preparing standards. Usually standards would be prepared with a standard that you purchase. Let's say you're going to prepare caffeine standard. So you will have, from that standard, you will prepare 5 different concentrations, known concentrations, and then you run them on the HPLC, and then you determine area under the curve for each peak. We'll learn chromatography next week. So you will determine area under the curve, and each area under the curve will be correlated to a concentration, and then you generate a linear regression and an equation of the line, and you use that to calculate caffeine in an unknown sample, like in a tea or coffee or Pepsi or whatever. So you use your standard curve to determine unknown concentration. Everything we deal with is usually proportional. So like the absorbance is proportional. If we're doing UV, absorbance will be proportional to the concentration. If we're doing area under the curve, it would be proportional to the concentration. So most of the things we do in the lab is really a concentration proportional to the measurement that you're doing, whether it's an absorbance or whether it's an area under the curve. And then in food analysis, mostly it's linear regression, what we do. Not quadratic, not to the power, I don't know, exponential. Only linear is what we'll be doing. So always you have your independent variable, and that would be your concentration, would be the independent variable, and the dependent variable is the measurement, whether it's an absorption or, let's say, an area under the curve. So your x-axis is always your independent variable, and then your y-axis is your dependent variable, and then you will have a coefficient, correlation coefficient, how well the data fits a straight line, and coefficient of determination, which is basically how good your prediction is using that standard curve, how much of the measurement is explained by the regression. That means prediction. So here's an example. This is a bovine serum albumin standard. It's a protein, and it's done for a protein assay. It can be either a Bradford assay or a BCA assay. I'm going to talk about this when we talk about protein determination. But in general, like I said, you prepare known concentrations of the standard, and then it's a colorimetric assay. So you measure absorbance at a specific wavelength. And then you plot, and usually use Excel to plot the standard curve, and you generate an equation and your regression, coefficient of regression, which is R squared. It's pretty good. We'd like to see 0.999, that would be wonderful, but 0.989 is still good. Most of your data points are close to your prediction line. And then when you run your sample, you get an absorbance. So you put in Y and you solve for X. X would be your concentration. And that's how you determine your unknown concentration. Aha, that's the fun part. So, significance figures. In your book chapter 4, you'll see you have a page or so on significance figures. Let's just give you some examples here. Okay, they have a few examples. How many significant figures do I have here? Okay. Sorry. 4. I can't remember your name. You're Bill and you're Drew. I keep mixing you up. Okay, 4. Yeah. So how about Christina? 1. So how about now?
4.
Nora?
3.
No. Tara?
4.
4. Yes. So when you have this, this becomes significant, significant, significant. So 4. All right. How about here? Sven? No. Joe?
1.
1. That's these don't count. Okay. Yeah. Okay. Let me do one more. What about this? Michelle, the back? Huh? 3. Yes. That's right. Okay. So this is easy. That's the easy part, not the confusing part. So you got that right. Okay. So let's say you're multiplying a series of numbers. So let's say you have 36.54 times 238 times 1.1. You get a value of 9566.172. If you put this in the table, you get deducted points, just let you know. Okay, so how do I determine how many significant figures must my answer have? Sarah?
You use the value of the least amount.
Yeah?
You would only use 2 significant figures.
Yes. So here you have 2, here you have 3, here you have 4, so you'll just use 2. So you round this up. So this would be 9600. So only 2 significant figures. That would be how you report that value. Okay, let me complicate things a bit. You did, you're going to do a caffeine determination, and then you determined your caffeine in a sample, and it was, this is not it. Okay, it was 43.5 microgram per milliliter. So you determined your value using regression, and in the sample A, you got 43.5 ppm, parts per million, microgram per milliliter. Okay, but you diluted your sample 50 times. So you want to determine your original concentration in your sample. So you need to multiply by a dilution factor. So now what? How many significant figures you should report? So your actual value is 2175 microgram per milliliter. So how many significant figures you should report? Yes, Nicole?
I'm gonna guess and say 3.
Why did you guess 3?
Because 50 is, it's just a dilution, it's not, I don't think it's important.
But if you want to think about this rule, and
50 doesn't have a decimal point,
it doesn't.
so you would go with 3 sig figs based on 43.5. So you would need
No.
218
No.
micrograms.
Mm-mm. How many significant figures do you have here? 1. So, Jenny?
Did you use a volumetric flask for your dilution?
Oh, that
Because maybe you're underestimating how many significant figures you should have in your
That's
dilution.
good. I wanted to fool everyone first and then get to that part. So I wanted you all to say 2,000, and then I'm going to say no. You lose the sensitivity here of your method. So if you use a volumetric flask, which we always do when we do dilutions, or mostly always, they have a tolerance level, or they have a certain accuracy. So they're accurate, especially 50 milliliter volumetric flasks are accurate to 0.05 milliliters. And this would be a rounded figure, so you want to consider the number before that, okay? So if this is, let's say, 0.15, then you would go one significant figure here. So you would report this as such. So you would report this as such. This means 1, 2, 3, and then you go, okay, I have 2180 micrograms per milliliter. And that's how you report your significant figure.
Why do you just use 1?
Because in the lab next week, we're going to learn about always the last figure is a rounded figure. Like say, if the balance reads 4 decimals after the point, the last decimal is rounded. So we only trust for sure the first 3. Okay. Any questions on sig figures? You'll have a ton next week, but this is just kind of to get you started thinking about them. It's very important. Yes, Cindy?
So if you don't use volumetric flask and you're using a pipette?
So then you'll use the accuracy of the pipette. Yes, very good. So you always have to look at the accuracy of the whatever you're using for dilution. Okay, what's the tolerance of that instrument? Yes, thank you, Cindy. Okay, I was going to say so the significant figure is going to haunt you in capstone. It's going to haunt you later on if you become a graduate student and you're reporting your data for a manuscript. It's going to come back at you. So it's good to learn about it. Or I'm sure you learned about it before, but now it's reinforcing the knowledge. Okay, reject data. So Q-test. It's a very simple test, and there is a table on page 65 in your book for tabulated Q values. Again, you select the Q value based on your replication and the confidence that you want, 90%, 95%, and the number of replications. So you get a value from that table. And then there's the calculated Q. The way you calculate it basically, let's say your x1 in this case is your random number that you got, which is very weird and looks very different than the rest of your set of data. So x1 will be your questionable data point. x2 will be the value closest to it. okay? So the difference of the value closest to the odd one over your range of the data. The range of the data, the difference between the maximum and the minimum, will give you a calculated Q. If the calculated Q is larger than the tabulated, so it's bigger than the tabulated, then you reject that value. Now, remember this, you're going to use it in different labs. For example, if you are determining the caffeine, or you're determining moisture, you're determining protein, and then you had 3 applications, one is really, really off, then it will skew your true value, how close it is to the true value. So you want to make sure you include this in your report and eliminate that odd piece of data. So what are we doing in the lab next week? Okay, so basically we're going to get you familiarized with using pipettes and balances and flasks, measuring utensils basically, because you'll be using them the entire semester, so it's good to start from the beginning and learn how to use them. And not just that, you're going to use these values and determine all the sets of statistics that we talked about, and we'll have discussion about them and the significant figures and everything. So in order to prepare, please read chapter 4 and we're going to use the lab manual. So not the packet, the actual food analysis lab manual. Please familiarize yourself with the safety and sources of error for the first lab that we're going to have in the actual wet chemistry lab. So you need to know that. There will be a pre-lab quiz. Of course, don't forget, bring your lab manual, notebook. If you don't have the lab manual, if you have your laptop, then you can access it online. You need your laptops next week. Please bring it with you, because we're going to do calculations in the lab. We're going to discuss the data in the lab, so that will save a lot for you later on when you're preparing your lab report. And come on time, obviously. I have 2 minutes. I want to do last week's lecture, and we'll just do a check since we have 3 minutes. So recap questions. Just to ensure that you learn the material. With the last 3 minutes that we have, we'll do recap. Okay, is nutrition label required for all food? What? Okay, let's raise hands. Where you, Sven, then? Go ahead.
Not for the fast food or the
Okay, so not for all, that's more packages. You were going to say something else?
I was going to say just like fresh fruit and vegetables.
I mean eggs.
Eggs.
Yep. Okay. What agencies regulate nutrition labeling? Andy.
FDA and USDA.
Okay, FDA and USDA. Do you know USDA specifically? What do they regulate? Do you remember this part? Joe?
FSIS.
Huh?
FSIS.
Yes, but what meat? What meat?
Yeah.
Meat, poultry, and eggs. I answered the question. Okay, never mind. What are new changes in the nutrition label? Tara.
They changed the vitamins, so I changed from vitamin A and C to vitamin D and potassium, iron.
Yes.
Are on there. They have an added sugar section.
Yeah, let's get some other people. John.
It means the television labels.
Huge in your face. Yes, Agnes.
Do you take away the total calories per fat?
Yeah, they took away the total calorie per fat. That's right. Okay. One thing, you say added sugar? Don't forget that. How much added sugar is now part of the nutrition label. What type of analytical methods are required to obtain the values listed on the nutrition label? Sonia?
Like methods from the AOAC.
Official methods of analysis, yes, like methods from the AOAC. All right, when can you claim calorie-free? Yes, Catherine.
There's less than 5 calories per serving.
Yes, very good. Is the label in compliance when an added nutrient level is 80% of what is listed on the label? And Drew, right?
Does that depend on the nutrient?
Huh?
Does that depend on the nutrient?
I can't hear you.
Does it depend on the nutrient?
No, it doesn't depend, just added, you added in something. So is it okay to have only 80%?
Yes.
So, Farah?
No, it should be like 100%.
It should be at least 100% or more. This is 80% or more, could be for the naturally occurring nutrients. Okay, so these are similar to what would the quiz true and false have? So, or an exam, such kind of questions. Okay, well, thank you. See you on Wednesday.